So friends, this is an example of a thermodynamic process, and the goal is to name the process and do a little math to calculate some things. So the example, first of all, for isochoric processes, remember that that's constant volume. For all of these, we can assume a constant number of moles. That's typically the case. So if V is constant, obviously here's kind of the summary, all right? To calculate actual values. And here's what I mean by calculate actual values like, say you just need to know the number of moles in something, but you haven't had anything change yet or anything like that. You use PV equals nRT. Great. To calculate something when there has been a change, use ratios. Right? And actually, I should add one more. Don't forget that PV equals nRT. And then, of course, E total equals 3/2 or 5/2, careful on which one it is, nRT, which means the change in energy in a gas will be 3/2 or 5/2 nR delta T, right? Where delta T is T2 minus T1. It's the change in temperature. So really, we want delta E total when we're dealing with a thermodynamic process. Let's just say 5/2, and that's an N, of course. What determines the energy of a gas? The energy of a gas is dependent on its temperature. Obviously, it's dependent on the number of moles, but if we're assuming that N is constant, that means if the temperature changes, the energy changes because they're moving faster or they're moving slower. So delta E total will depend entirely on delta T. That's really important. That's going to become really important when we want to understand how lots of things work, is that the temperature change is the energy change given by this formula. So for an isochoric process, constant V, that means that P1 over T1 equals P2 over T2. And for an isobaric process, constant pressure, we have the volume changing. V1 over T1 equals V2 over T2. And then there's one more we're going to do today. That'll be the next video. Right? But for today, here it is. Let's practice. So example. I have 600 milliliters of air in a bottle. Right? And it's initially at 300 Kelvin. And then I put it in the freezer. For those of you in class, I did this in class. Temperature 2, we'll say, is 270 Kelvin, a little below freezing. Remember, freezing is 273.15. Great. It's in a flexible container. What is the type of process? Right? We can draw the mechanism. We kind of did that in class, so I'm just going to do the numbers here. Since it's flexible, I'll give you a hint. The volume can change. What are the new values of pressure and volume? Or should I say the final values? pressure and volume, and what is the change in energy in the air, in the bottle. All right, here we go. Pause it if you want to take in the questions. This is it. All right, so first a few ratios, right? So if it's flexible, V can change, which will equalize the pressure. Because remember, if I put it in the freezer, the whole point, I'll draw a little diagram here. This is my rough diagram. Your diagrams might want a little more detail. If I put it in the freezer, it gets a low pressure inside, right? If it drops to 270 Kelvin inside, it initially was, and it's sealed in the top, right? It initially was 300 Kelvin. That's going to drop the pressure, right? Because slower. So fewer collisions and less energy per collision. So what I said out loud is what you would write and draw and make sure you understand that. So what's the whole point? Well, if I have a low pressure outside and atmospheric pressure inside, I have a delta P pointing in. And delta P times the area will be the net pressure force on the bottle. Now, if the bottle doesn't have any force to fight back with, there's no rigidity for it to fight back with, this will be the net force on the bottle full stop, and that will squeeze the bottle, right? This will squeeze inward. I have a delta P inward because it's lower pressure inside, because it's colder, therefore it's slower, therefore there's less pressure, fewer collisions, less energy per collision, great. But that will decrease the volume. But lowering the volume, that's like part one, squeeze the bottle inward, so V drops, great. Part two, though, is that lower volume means a higher pressure. That increases the pressure. So the last final stage is like a smaller bottle. Let me draw that a little better, right? A little smaller bottle, right? It's kind of squeezed in, lower V, but there's 1 atmospheric pressure inside, because it will keep squeezing it until delta P equals 0. So the final stage is that the pressure is atmospheric pressure. So this was isobaric. Back to 1 atm. Now, this pressure in different examples might not be 1 atmosphere, but clearly if I put a bottle in the fridge, it's surrounded by atmospheric pressure. So in this specific example, it is atmospheric pressure. It might not be the case always, but in this specific example, it is. So stage 1, it was slower, therefore lower pressure inside. But stage 2 is that it lowers the volume because of the lower pressure, which increases the pressure back to atmospheric pressure. So therefore, we just have a lower pressure. V1 over T1 equals V2 over T2. That is isobaric cooling. We have an isobaric cooling here. And then let's calculate it. So V1 was 600 milliliters. T1 is 300 Kelvin. V2 is the question mark. T2 is 270 Kelvin. If you see the ratio, you might be able to do this in your head. This is a 2-to-1 ratio, so therefore this should be 540. But we can set it up. So you might say, don't we need cubic meters? In ratios, units don't matter, except for you need Kelvin. Except Kelvin. The reason that Kelvin matters is because it's an additive. So if I do K equals C plus 273.15, this is not a ratio. This is a additive conversion, not a ratio conversion, not a multiplicative conversion. So since all of the conversions are multiplied by 1,000,000 or multiplied by 1,000, right? I would divide by 1,000,000 here, divide by 1,000,000 here. I get the same thing on both sides. So I do V1 over T1 equals V2 over T2. If I do milliliters here, I need milliliters here. So when I say they don't matter, they just need to match. Just need to match. Because if I were to convert to cubic meters here, what would I do? Divide by 1,000,000 on this side, divide by 1,000,000 on this side. Same thing. If it's a ratio, that just cancels. Ratios are so great for that. It's the only place where you don't have to convert. Yay! You don't have to convert. You can just stick with milliliters. We do need Kelvin though, but I'll give that to you. That's easy. So let's set it up. So what do we have? We have 600 milliliters over 300 Kelvin equals V2 over 270 Kelvin. You get that V2 is 540 milliliters. Simple 1-to-2 ratio, volume to temperature, volume to temperature. We check our answer. Should it be smaller? Yes. It is squeezed by, what is that? 9/10. It's squeezed by 10% less. 10% less volume. That's it. So that's the example and how you use numbers to do this. Now I should, oops, I forgot to do the last question, which is, what is the delta E total? Delta E total is, well, it was air. So that's 5 halves NR delta T, where delta T is T2 minus T1, which is going to be 270 minus 300, which is negative 30 Kelvin. Negative is important. We need to plug the negative sign in because delta E total is negative. Negative why? Because cooling. Right? It lost energy. So that negative and positive is going to be so important. Right? Now, what caused this in the first place, if you remember, was there is a heat transfer out of the bottle. So Q was negative. So what causes is we have a freezer, right, that's lower temperature. So via collisions, this is a heat conduction, powers isobaric and isochoric processes. Right? If it's cooling, Q is negative. If it's heating, Q is positive. Remember that heat conduction, positive or negative Q, powers all of these. There is something else going on that we haven't talked about yet. But Q being positive or negative, we can start to understand. We don't have a formula for it yet, but we will eventually. Just getting that, throwing that in there in the background so we're thinking about it. Anyway, so this is negative, which makes sense. It's cooling down. Smaller number minus bigger number. This is going to be negative. Great. So let's plug it in. 5 halves. Oh, wait, what's N? Here's where we go, right? Here we go. So P, here's where we use PV equals nRT to solve for N. Right? So I do the pressure, which was 101,325 pascals, times the volume, which was 600 milliliters. Now I do need to convert, 600 milliliters into cubic meters. That's going to be 6 times 10 to the negative 4 cubic meters. Maybe you want to convert all the time just to make sure, right? So you have to convert to cubic meters, right? So 0.0, 1, 2, 3, 4, 5, 6, 0, 0, 6, 1, 2, 3, 4 cubic meters. PV equals N times 8.31 times Kelvin, which is 300 Kelvin. Make sure you correspond V1 to T1. Please don't plug in V1 and then plug in 270 Kelvin for T2. Oops, I wrote T2. Please plug in V1 corresponding to T1. It doesn't matter what you use. The point is, if you plugged in 540 and 270, you get the same result because that's a ratio, right? So make sure you plug in the correct, appropriate, corresponding volume and temperature for this. So I'm going to get N equals, calculate, I don't want to do that in my head, 101,325 times 0.0006. Make sure I have the correct number of zeros. Take a moment. I have 3 zeros, 3 zeros. Got it. Divided by 8.31, divided by 300. So I get point. And you probably want 3 decimals. When I say 3 decimals, I mean 3 numbers that aren't 0. So 0.024386. I can even write all that just to be exact. Let's say 0.0244. That'll work for me. Moles. Got it. So 5 halves, 0.0244 times 8.31 times negative 30. In fact, I'm just going to copy this number into this. So I get this times 5 halves times 8.31 times negative 30. And I get 15 negative 0.198. So basically 15.2 joules. And that's the answer. Exclamation point. Not that much. Remember, we're dealing with usually the hundreds of joules or the thousands of joules. But this little bottle of 600 milliliters, which isn't much, that's just a little bit of space, got squished a little bit and therefore lost 15.2 joules of energy because, not because it was squished, but because it was losing energy due to the heat transfer outward. So Q is not this. Careful. This is not Q. Careful. Right? So this is delta E total. You might say, wait, why isn't that Q? Well, we're getting there. Maybe we can start talking about it this week, but we need to get through these calculations first. So delta E total, it lost 15.2 joules of energy. I'll give you a hint. The squeezing actually added energy. Ooh, people have been talking about that. That's method 2. You squeeze something, you give it energy. So the squeezing actually added energy, which means it had to lose even more than 15.2 joules to make up for that. We're going to get to that after Thanksgiving break. Here's the answer. Here's the volume. Here's the number of moles. Here's the delta E total. Got it. Rewind if you need. Ask questions in class. You guys are amazing.